Okay, so pleasure to meet you all, and especially because you are all people that, as Alan explained to me, that understand the SES, because mostly I do presentations to people that don't. So, yeah, this is kind of a different one for us at Aircat. So to present myself, I'm Eduard Ercegovic. I'm master's degree in nautical studies. I was a captain on big commercial vessels from mega box ships, and then later to offshore supply vessels. From that, I moved to working onshore, supplying a whole set of different vessels, from offshore supply vessels, IMRs, crew boats, and so on, in Angola. So I was a fleet coordinator, fleet technical, and base coordinator, support base coordinator. So there was a lot of meetings with clients and discussions and raising, resolving issues, and so on and so on. From there, kind of learned about the market and what was required, and where the issues are, at least on this West Africa region for the oil and gas marine vessels. Um, There also I work with my colleague Jerome Arnold, who is managing director of Aircat. And then we were trying to find a solution to the crisis that broke out at that time for oil and gas, where all the vessel rates went down except for the big crew boats, because helicopters were stopped due to crashes and also due to lack of funding. And crews still need to go to offshore to join their platforms. So we identified that there is a kind of a big gap that could be filled if we could find a better solution, a better vessel to replace the legacy crew boat designs that were in use at the time. So that's where we parted with ESNA, and we identified that SES is one of the concepts that is ready and available, uh, that could be built because that it's a not new concept. It existed long time. Just it was not applied because people got comfortable. They were using the legacy vessels, mainly monohulls in oil and gas, for the high-speed transfers for long-range crew boats, and in the end they reached their maximum. So basically, the ones that we are replacing today are in the range of 35, around 35 knots, and basically a standard monohull. So there's nothing new about it. They were basically same vessels from how similar to torpedo boats from the Second World War, that they just changed and added jets instead of the propellers. So there we identified ESNA, and we were very happy with their response. They are experts at what they do. You all probably know them. So we kind of had very good cooperation, and that's why we decided to partner and create a vessel that is going to be more efficient, faster, more comfortable, and also tick all other requirements, particular to the industry, also particular to the area of operation, which is West Africa, meaning there are no proper shipyards. So all this said, we kind of set requirements that we had to meet, and we worked. That was in 2016 when we started, and we had already initial designs in 2017. And this evolved until we finally convinced the end client. So not the shipyard, not the owners. We also tried that way, but end clients were important that they actually could have something that is better than what they are using then. So until today. So what we came up with is a Aircat 35 design, and for particular uh, targeted contract that today started to work. So from beginning of year, we have now 3 vessels working in Angola. Is Aircat 35 design. We call it Crewliner. So why the name is for like that's okay. Aircat is the name of the company, Aircat and Catamarans. 35 is a 35-meter class, so length of the vessel, and Crewliner is a version of the vessel that has increased space for passengers and a little bit of cargo deck. We also have some other versions that are not built yet. There is like a combi, which would be with increased deck on stern and stern console with a smaller deck house moved a bit forward, so more like a super fast platform supply vessel or FSIV. And also we have a project for a max specs version, which would be maximum passengers for commercial passenger transports. So something that would go against ferries. So ferry SS. Also lately, this is what we mentioned just before the meeting started. We also partnered with some other, let's say, partners from US to create a military version, but based on the same existing hulls that we have already in use today. So we created Eureka, which is partially also owned by Aircat as a company. So the new company is promoting only naval version of vessels and paramilitary version of vessels, but the main product today from Eureka is called Bengal. Bengal is actually same this vessel, Aircat 35 hull with the military version on top of it. So basically under deck is 95% identical. So the vessel itself had to be built to meet the specs of the end client. There were some special requirements. A part of the SES itself, it needed to be also comfortable. It needed also to be easier to maintain, which kind of conflicts with the SES because SES is more complicated than legacy vessels. So I don't know if you see my screen now, top view of the vessel. Do you?
Yep.
Okay. So some things that ESNA as a naval architects that were leading on this on the naval architect side is that they made it significantly wider. So this vessel is 35 by 13.9 meters. Also, it widens as you go towards the stern because we had to fit very powerful engines. We had to go for 4, revise that. Now, going back to requirements from the end client required minimum 3. And because it's a catamaran, we had to go for 4, of course. If you see on the picture, on this top view, that it has also hatches. So above each engine had to be a hatch. And because we had to design it as a plug and play, because there is no shipyard that is readily available. There are some docks that are mainly, maintenance docks. So we had to have hatches that we could come alongside, take out the engine, and put the spare one in, set some programming, and vessel is ready to go. Why is that? Because originally it's three vessels that need to cover whole area of two production blocks for Total Energies in Angola, and that's actually a minimum number of the vessels that they would need. Probably they will go for fourth one, but they cannot afford to lose a vessel for a long period of maintenance. So we had to put the hatch above and every main engine. So main engines are actually one astern and another. They are not next to each other, also due to slimness of the hull. We have a hatch also above the airlift engine, which is here on a bow side of the hulls. And we also have big hatches for the lift fans itself. So also other requirements that we had to have form of the vessel that satisfies offshore rules to receive the cargoes on the bow, like from the platforms. So there are some clearance requirements, and then we had to also dimension the bow area to receive personnel transfer devices like frogs and stuff, where you have a minimum landing area and clearance area and then approach areas. And so all this was defining actually how the vessel is going to be shaped and final looks of the vessels. Also, you might not notice on the bow there is this kind of nose tip sticking out. This is actually because this vessel is doing transfers offshore, so people are transferred through the boat landings. These boat landings are, let's say, similar concept like the boat landings on wind farms, but they are somewhat bigger and stronger, and they do not use the flat shapes. They use four pipes in V shape. So a vessel pushes into it and then kind of creates a friction to the pipes so the vessel does not slide. And then people just step out onto the vertical ladders and climb on the structure, go into the structure, climb to the installation, and same way back. So going further, vessel also had to meet some requirements. You might notice here that the vessel whole superstructure, whole deck house is not attached directly to the deck of the vessel. It's mounted on resilient mounts, so basically rubber steps. Why was this? Also coming as one of the requirements from the end client, but also it kind of increased the comfort of the vessel a lot because there are no transfer of the noise and vibration. So these resilient mounts allow a lot. Also here on the side, you can see hatch. This hatch is here for the gensets. It has two independent gensets. And suction for airlift system is also here on the side. These two openings, and in between them, it's a lift fan area. What I want to say now, choice of machinery, choice of equipment, and everything. At Aircat, we had decided that our experience showed that there is a big gap between the shipyards and the designers that they work with and clients that need to use the vessels. Owners that are in between are basically forced to offer what the end client wants. So there was very little space to offer something new. So our approach when we were promoting and marketing this, we tried different ways and we concluded, like I said in the beginning, that you need to actually come to the end client the one that is financing everything, that is paying for the vessel, and make them understand what they can get and what benefits they have if they use such a vessel. So when we came to Total Angola, uh, because we worked there, Jerome and me, we were very experienced on how they were doing business. We were actually also chartering these vessels, partially not directly to Total Angola, but to some others, but same vessel that they use. We were using these vessels personally, so we knew a lot about them. So we were there. So they had a big issue. Their issue was how to transfer people that come from the airplane in the morning, like 6, 7 o'clock, that lands in Angola, in Luanda airport, to bring them to port and to bring them to the field, and then the off-signers to take off the field and come back to fly out with the same airplane in the evening. That was just not doable because the block 17 and 32 that they operate is 90 to 160 miles from the port. Different installations. There are currently 6 big FPSOs, and they have like around 150 personnel on each one, depending what they do. If they have done some maintenance, that can go up to 600, and additional vessels that are around and so on. So for them was big issue because they were going further and further, deeper and deeper with the new installations, with new discoveries, but their vessels were not following. And even the vessels, as they get older, they were kind of getting tired, and they would slow down, and they had more and more issues, so they had to slow down due to various structural problems and so on. So we came and said, look, we can give you a vessel that is going to be 30 to 40% faster than what you use today, with same capacities, with better characteristics, that is going to be more comfortable, that is going to be more safe during transfers. People when come there are going to be less tired, okay, because the vessel is more comfortable, the ride is more comfortable, and you could do all this in one day. So apart that you are going to save on fuel, you are going to have also people that are more prepared to continue to work as fast as possible because they are not going to be vomiting as much during transfers. And also, you don't have to pay one more day of salary, one more day for hotels, meet and greet services from the agents, and all the problems that you might have with the paperwork, because these all people need also to regulate the visa, extend the visa for the days that they stay ashore. So that kind of made them interested in what we were offering. And when they actually made the first tender to replace the current vessels, that was in 2018, they were actually asking for same vessels like they have, these monohulls, with some improved qualities, but nothing to do with the naval architecture type side of the vessel. It was just more internet, more I don't know, some this kind of stuff requirements. But a part of the standard form for tendering, they also asked for alternative solutions, and they were asking for more than 40 knots for alternative solutions to the standard tender requirements. And that's where we actually got our opening to offer Aircat 35. At that time, we were calling it Quad Boost. Quad Boost was because it was a version design, and Boost was with the more powerful engines, because we were offering 1078 kilowatt engines, and the boost was this one that actually was built, Aircat 35 Crewliner in the end. It is 1440 kilowatts each engine from MTU. Okay, so that made Total interested. Total was engaging there on world level now. Marine departments from Paris, and they engage also some external people to advise them on this, and took them almost 2 years to kind of confirm that actually, and to make sure that these vessels are what we say, because for them also numbers were kind of, I guess, surprise. So they, after 2 years, they confirmed that they want it, and story started there. There were some complications with the initial tender. The tender was repeated, but actually, when they repeated the tender, they actually were asking for these same vessels, but just to be offered through other owner. And in the end, final contract was signed in 2022. Uh, ship Ship owner chosen on our advices, but of course taking account all the financing and all their planning. Shipyard. Shipyard was chosen Strategic Marine, and these vessels were completed by end of last year, and beginning of this year they were finally delivered. First one was actually delivered around Christmas, and last one was delivered in end of February. So 3 vessels that are operating now. However, they have some baby issues, but nothing really connected to the concept of SES. Mainly, there are some electronics and stuff that still need to be fine-tuned. We have something like unexpected failure of automatic voltage regulator on a gensets, with kind of damage some other equipment, but that's nothing to do with the concept of the vessel, design of the vessel. That was failure of the genset maker. So yeah, the vessel itself, I can scroll through some views. Okay. Design evolved as we were going through the requirements. Some things were also adapted to the requirements, to the classification of the vessel, because it had to go, like we said, up to 200 miles offshore. It had to be classified as a high-speed craft. It had to satisfy also Sea Area 2 from BV requirements, that's up to 2.5 meters waves. We know that vessel can operate in higher waves, but that was some class requirements from BV. We didn't have to go higher than this, just to the nature of the area that the vessel is going to work, because as per class that would require some more weight of the structure, because that's the only change actually. They would just require more bulkheads. So yeah, the vessel itself also, this is what I said, we had to set up also our rules how we are going to operate. And like we said, we identified there is a gap, that clients are not aware what they can have. The shipyards are building what the owner orders. They offer something, and owner will order only something that he can for sure sell to the end client. So we had to kind of tackle in between all of this and make them understand that this is better and you can have it. You just need to ask for it. So in the end, they asked for it, and owner that decided to build it, it's AAS, before known as Petro Services, now known as All Energy Services. Yeah, going green. We also had decided that our approach is going to be very much different to what is usually done with when the vessels are built. So what we saw, you have designers that design a vessel, and I mean naval architects or whoever it is. Uh, they sell their design or license to build to the shipyards. Shipyards build the vessel. They decide mainly between them and with the owner how they are going to build the vessel, what equipment they are going to put inside, and then they offer it on the market to the end clients, and then end clients actually get vessels that are more or less the same, some
More or less, yeah.
variations,
More or
but
less.
they uh, they cut the costs on a lot of stuff. So we just said no. We still want to have control of what
Equipment.
the vessel is going to be, how it's going to be built, and also follow up in the use of the vessel. Yeah. So we actually, when we made a contract to the shipyard that was chosen by the owner, we said, look, this is a design that we are giving to you, but we specified the type of the engine, exact model, type of the jets, type of the navigation equipment for each piece of equipment. And we defined as much as we thought at that time. Lesson learned today, when the three vessels are built, our opinion is that we should define more. Yeah. So, so saying about this choice of equipment, we said, look, this vessel is all about efficiency and performance, and this is how we are selling it, and this is what we want it to be. So when tomorrow these vessels are built, they need to perform, they need to be as we promised. So we were kind of doing a lot of studies on what equipment we should use and what type of equipment it should be. So the main propulsion engines, we decided, okay, first we need the efficient engine, of course. We don't want to have any PTOs. We want maximum efficiency from the propulsion, so it's engine, gearbox, shaft, jets. Of course, jets were chosen due to speed and all the other characteristics that we require. So further on this, the target was these vessels, they need to operate 5 days per week, uh, 10 hours per day at very high speed. Because our target is we wanted to offer a vessel that is going to be in mid 40s when they operate on average. Okay. Trials were done in 2016 on a hull model, partially financed by the Shelf GOM, that's a Shell USA, because they were also at that time looking on how to substitute helicopter transport and also be able to evacuate big number of personnel in a case of hurricane or some kind of emergency like this. So they finance model testing. Model testing proved that with the engines that we wanted to have, with the power that we want to have, with the bollard push that we had from this set of propulsion, these engines and water jets, that we could have speeds above 50 knots. So when we were kind of presenting our vessel, we need to have some insurances, so we cut it, and actually the end requirement was 47 knots from the end client, but we knew that the vessel will be expected to do above 50. So again, going back, when we choose the equipment, so the gensets had to be independent, and because we have two hulls, we were just going symmetrical, and also we wanted to have a redundancy. We actually wanted to have redundancy on everything, but we needed to kind of balance always due to performance, need to be light, but we need to redundancy. We are going to work in harsh environment, high temperatures, low maintenance support. So all this we needed to put together. So choice went to MTU 2000 series engines. Why? Because they could provide a relatively compact engine, not too heavy. So we are talking about 3 tons per engine. And they could give us output power that we needed. So for a 50-knot vessel, we needed somewhere around 1,440 kilowatts on each engine. And importantly, due to operational requirements, like I said, 5 days per week at 10 hours at high speed, we needed engines that are made to work at 100% MCR, because that's what we expect and that's what the vessels are doing. So they're not operating at 85%, 70%, 80%. No, they are going full RPM. So the shafts also had to be carbon fiber shafts, not to have extra weight on this. So they are Senta made. Choice, there were several kind of options for a jet propulsion. In the end, we went with Kongsberg because we also had an option that tomorrow we need a vessel that could have dynamic positioning. And Kongsberg was the only one ready to offer this, and this vessel could have it just because it has 4 jets. Okay, the station keeping capability would not be at the level of the platform supply vessels that are DP class 2 or something, but would be capable to hold position, hold direction enough to receive delicate cargoes from the cranes while maneuvering near the installations, okay, or holding position near installations. So we went for Kongsberg mainly on this reason, and also Kongsberg tables were showing very good results, and they gave us all guarantees, so we were convinced with them. On airlift system, so airlift system as complete systems are provided by ESNA, and they are built by ESNA. So of course, whole vessel was set by ESNA, and because they are actually, in my opinion, the best at it today. And in the end, it proved we have results that are standing by it. So we needed to find a solution for the engines that are going to power the lift fans. Originally, we were going for Scania engines just to due to their compactness. Okay, because we needed an engine that is above 350 kilowatts. In the end, owner suggested that due to their experience with Scanias and MANs, that they prefer MAN engine. So we had to switch to MN, which were somewhat bigger, more powerful, and actually that proved to be a good solution, because bigger engine, more powerful engine resolved one of the issues that we had that shown during testing of the vessels when they were already built. So we kind of expected it. So the issue is that now we have a 478 kilowatt engine and we needed above 350. So we had to limit the RPMs of the engines. So engines can do 2,100. We limit them to 1,850 because that's the upper limit for the lift fans. And the gearbox ratio that we use on this vessel is 1:1. So ZF gearbox paired with the MAN engine powering the lift van. That's the combo that we chose in the end. The problem that we encountered was when you start up the lift fan engine, lift fan system, the engines were kind of on the limit of the torque and power that they can supply at low RPM. Because the startup of the lift fans until the lift fans came to speed, there was a lot of resistance or a lot of torque required that engines did not have because just the power at the 700 RPM was low. So we kind of suspected that we might have these problems. Initially, it was solved by increasing the RPM of when you clutch in the lift fan on the gearbox to a maximum that gearbox allowed. That was 1,000 RPM. So we set up the system when we started. We start the engine, so they're running. So you decide to activate the system. You need to clutch in. The engine picks up to 1,000 RPM and then clutches in. We were still getting some instability. So out of 10 starts, we had like 3 fails, let's say, on average. But it's still, of course, we were not satisfied because this was a bit forced clutched in because now you are on a limit on gearbox allowed RPM. Engines are providing more power and it's still not smooth. So in the end, we solve it by installing a trolling valves on gearboxes. And with these trolling valves, we added a sequence how the signal is going to be sent to trolling valves following the change in RPMs and give enough time for the lift fan to speed up to get to the same speeds as the engines. So we do not have this kind of non-synchronized start, and the start just become very smooth. On the other vessels, like for example, Seawind Pioneer, that was also built on ESNA, they didn't have these issues because it was a electric motor that was used, and as we know, electric motors do not have problem with the torque, while the diesel engines do at low power. And also, we also needed to clarify with the maker of the engine, with the MAN, to change the settings on the engine because they automatically set up the engine to be the finest and non-smoking or whatever to minimize all these kind of environment effects or at least visual ones, not really changing the efficiency of the vessel. So, for example, the engines had so-called smoke settings, and you had like 1, 2, 3, and this is connected to the IMO Tier 2 emission controls. So all these settings are still within the IMO Tier 2 requirements, but they were set to minimum. So we also had to adjust this to make sure that we have enough power just for this short time of start. Because after you start the lift fan engines, you're not going to use it same like a truck because basically these engines originate from truck engines. towing truck engines, big ones, because basically you increase the RPM, you lift the vessel, and for next few hours of sailing or 10 hours of sailing, you don't change much RPM on the lift fans. That's how the system was set up. Okay, so that was one of the main issues and the stuff that we learned when we were first testing the vessel, especially the first one. But we were already expecting that we are going to be on the limit with it, and we solve it smoothly by adding trolling valves that are going to regulate the clutching pressure, and also creating a sequence that will allow time for a lift fan to come to the same speed to the engine and to have a stable startups. So instead of having a startup that is going to last 30 seconds after the engines are warmed up already, we have a startup that is sequences in about 2 minutes. That's a difference, and that's a consequence of using the diesel engines instead of like on Civic Pioneer, for example, electric ones. So also we were requiring that all the equipment, as much as possible, to be off-the-shelf equipment. So we did not want to have custom-made gearboxes, custom-made jets, whatever. We just wanted to use the best equipment that is readily available with no special modifications. Or if there are any modifications, to be a minimal one. So, like for the jets, we had to slim up plates a bit before installing them, because Kongsberg leaves, it was like 3 inches on each side. We had to cut for an inch so they can come closer together. So stuff like this, and nothing special. So on this view, what you see is actually how the vessel is built, because this is the latest update that we have. So you all know SESs. So standard big openings are inlet openings, and there are lift fan inlet damper. Next to it, there are outlet openings, small dampers. These ones here. I don't know if you see my cursor. So yeah. So the smaller ones are actually used for recirculation and outlet. On the stern, the two central ones are actually also outlet dampers, and two outer ones are actually air supplies, tunnels, and inside there are electric motors to increase the pressure in the stern back. So as the SES, there was nothing special modified about it, except I would say advanced system from Messna, which is actually based on ones that they have on they made for a Civic Pioneer. They just built on this. So because now all the dampers were changed to electric actuators, so there is no hydraulics. The stern bag motors, fans are also electric motors. For example, even the care was taken to not to have any bolts and stuff in dampers. It's all on circlips due to vibration issues that we don't want something getting loose. Going on electric components, also given easier control of how these components behave. So we could have instant control and more precise control on how much the dampers are opening and how fast they react. So we have different speeds of opening, and then we could more precisely control the percentage of how much we open the dampers. So combined with this vessel uses six pressure sensors in a tunnel. So four in the main cushion area, two in a stern bag. So there is a lot of redundancy because basically you need one in stern bag and one in main cushion area for system to function. But all this input goes to the SES control system built around the Siemens PLC with the software that controls it. So with testing and everything, you had a lot of adjusting. So you have presets for ride control, presets for motion control, ride control, what we call control of the pressure in the air cushion area during high speed. And the motion control is control of the pressure and how it reacts to the change of pressure and movement of the vessel during the boat landing transfers or when stationary. So a part of the pressure sensor also we have in a center line just under the wheelhouse we have mounted the MRU, so motion reference unit. So input from combination of input from pressure sensors to motion sensor gives actually information on computer how it should react and how it should open or close the primarily outlet dampers. Yeah. So further on this, we had to also have a lot of ergonomics problems solved. And then we decided that the organization of the bridge is going to be more of the cockpit size, cockpit style, sorry. And because originally we had only three persons that are going to be on the bridge during high-speed transfers or any critical operation. One is going to be an engineer, which is on a port seat. I'm just going to show you this in a moment. Center seat is of course the pilot of the vessel, and on the starboard seat is another deck officer who is going to assist mainly captain or pilot of the vessel on how whatever he might need during the operation of the vessel. So I'm just going to switch screen. Give me a moment. Okay. I can show you now. This is actually a preliminary, uh, uh, let's say, side tour of the vessel. We still don't have a final one. This is the vessel number one before she left the shipyard. This is a strategic shipyard. Here you have number two next to it, still being painted. This one was already on a final testing phases before delivery. So, okay, the bow tip, bow nose. This one is actually modular. We can change it to a different style if it's required. We can go closer. Okay, so this is actually access to the lift fan engine. This is a lift fan engine ventilation. It had to be lifted from the deck as per class requirements. Also, you can see that we had to shape a little bit aerodynamics into the forward part of the superstructure to kind of minimize the windage effect. But also we have some complications as the vessel was required to have the latch system. That's why you have this red piping going around. This actually added a lot of weight and a lot of complications. And actually, we have a PTO, but that PTO is a large fire pump just to have enough water, which is 300 cubic meters, to supply everything that the vessel can actually approach the platform in case of fire on the platform and receive people to evacuate them. So that was one of the conflicting requirements with being light and fast. But that PTO, again, like we said, we didn't want to PTO anything because we wanted maximum performance from the propulsion. But that PTO is only used when vessel is basically stationary or slow approaching the platform just to get the protection. Okay, so the hulls are very narrow, and this is one of the bad sides of the vessel, but it's a compromise that we had to make. This is a MAN engine that is powering the lift fan, and you can see that the space is very tight. However, we had to do some modifications also due to tight space, that we had to kind of put out the filters so they are easily reachable and stuff like this. So we had to still have a minimum everyday maintenance capability on these engines. But for any serious work, like we said, even in contract for the owner was given that all major components of equipment, they had to have at least one spare per 3 vessels. So that's why the owner, a part of the 3 vessels that are working, they have a spare jet, they have a spare main engine, they have a spare gearbox for the main engine, they have spare gearbox on the lift fan engine, they have spare lift fan, and they have a spare lift fan engine. So a part of all the also other things like controls for the SES, control cabinet, uh, drives for the stern bag fans and stuff like this. This critical equipment was all kind of set to be plug and play. So in case that you have issue, you don't repair, you don't stop the vessel for a month, because that's what you are looking, you just to get the personnel to maintain the vessel, they need to come to Angola. And that's already an issue because you need a visa, you need the tools, you need everything. So that takes time. And just for this, we needed to change the whole concept how you operate the vessel, because we just said, okay, look, we don't have time to kind of change the parts or do some tuning of the engine. You just take one out, put one other in, program whatever you need in controls, test it, and after a day or two, you're back in business. Okay, so yes, that's one side of it. Yes, you can go here. This is other side of the engine. You can see here, this shaft is a shaft that goes through the watertight bulkhead of this engine room and goes to the lift fan. So it's very tight business. It's very tight space, and also we had the big requirements because we have all these powerful exhausts, mufflers mount on it. So it's not easy. Engineers are not very happy, but yeah, that's what we had to do. So I can show also here the lift fan room. Okay, so this is watertight bulkhead. There is the engine behind. This is a lift fan. It's a fan systems width make. Okay. Um, Here you have a dampers. Okay, this is an outlet damper, and here is a inlet damper, the big one. This space is basically like other SESs, it's not considered as inner space, it's outer space area. What we had to add to make sure that we don't have a lot of water setting in, because there is a lot of water coming in, especially with the water spray and stuff. We had to have very serious bilge pumps on this side and the other side, and they are on a automatic system of, so they activate high-low alarms, high-high alarms, and so on. So this all had to be adjusted, and because we could not have any drain openings here on this side, because it just would create more problems than resolve stuff. So going around the vessel, I can show you here. Okay, so these are the ventilations of the main engines. So stern, inner engine, forward engine. Here you can see the pipe of the large system. Some complications we had because of the cabins and separation from escape routes which are outside, and also the passenger area where you have big windows require the A30 isolation, and that also create a lot of modifications and problems for us, because then we had to change the insulation materials, change the type of the windows. So instead of having nice windows, we had to go for a small ones, and they are A60. You can see here all the way around the large area, the large spaces. Okay, the here you can see the line, and actually this is a hatch that you lift together with the ventilation of the engine room to get access on, and you actually have a clear on top of the main engine. There are no bolts or whatever, because the strategic marine shipyard had a very nice solutions that is catch from the underside, and it's sealed by the rubber seal. So when you want to open it, you just take a knife, cut the rubber, unbolt it from under, and you just pick up the ventilation and the hatch, and they have full access to the engine, so you can just lift the engine relatively easily. Okay, so inside of the engine room, okay, this is the space of the engine room. Also not a lot of space, but better than lift fan engines. These are nice MTU 2000 series 16V engines. Let's go. Okay, this is the other one. So I will not get into too much detail there. I need to come out of this. Okay, where is it? So also we had to kind of find spaces for equipment like this. Uh, Originally, we were planning to put it on top of the roof, but then the class required that to be uh, closely accessible, easily accessible from the main deck. We had to have a MOP system that could be released from the bridge, so not that you have to go directly there. So all the life rafts and MOB light buoy had to be remotely released from somewhere near the wheelhouse. Okay, some fancy stuff like permanent storages for fenders, because we remove all the rubber fenders around the vessels because they're just too heavy, and opted for these removable ones. The air conditioning system was is actually marinized split system. There is no big water cool or whatever, and also goes on operating area, because it's just easier to maintain them. If your unit have issues, you are just going to swap them, connect it to the existing pipes, and you are ready to go. If you have a big system, it's probably more effective, but it creates a problem. Here on stern, we just have some storage spaces, nothing, just for tools, ropes, and stuff like this. And this is a stern entrance to the vessel. So these are cabins. They are kind of relatively, they're nice, but minimum. Sorry. So they have each cabin is equipped, so two bed cabin. It has a actually very fancy equipped bathrooms, because you see they have actually glass cabins and stuff, which was totally unexpected, but this is what the owner wanted. They also have a dryers on top of the wash basins and stuff. So yeah, we have three cabins, each one with two beds. We have a laundry room here. Basically, this is supposed to have, still not installed, it's supposed to have two washer dryers, dual units. It goes into the, sorry, goes into the comfort of the crew. So this is one more cabin. On the other side, there is one more cabin here. And then we have here, these are passenger toilets, two identical ones for 80 passengers. And this is a passenger saloon. There had to be a lot of ACs, so you can see six ceiling units, very powerful ones. There is ambiental lighting, adjustable. The seatings are business class for a crew boat. This also complicated things a bit, but we managed to do with the seat designer, seat maker, optimal spacing. So 80 passengers, and the configuration is basically 3-4-3. So each passenger has USB chargers, lights, and leg rests, tables, and so on. The vessel is equipped with a high-speed internet. They have double Starlink antennas, and as a backup, there is a VSAT, and there is also Iridium. So this was all high-end requirements that, like I said, came from the operational vessel. So basically, for passengers, it's very comfortable. They can kind of have a half lying down with a leg rest. They can charge their phones, tablets, or computers. They can have reading lights. They can connect to the system on board, and you have like that movies and whatever you needed. Same like on airplanes, just to use your own screen. Okay, that's okay. So this here is a passenger lounge. I don't see the great use of this area because it's relatively small and not like passengers are going to use it. Like on 80 persons, maybe 3 or 4 can sit here. And we have like coffee machine, we have vending machine, but that was owner requirements. Originally, it was just supposed to be storage area. This is a crew mess room. Here also there is a main switchboard. Here is an access to the engine rooms that you don't need to go outside, which is obviously problem going at high speed, that you can access from the center of vessel, go through the tunnel, and then you go port or starboard hull, and you access the engine rooms. And you actually come out to forward engine rooms, and then from the forward engine rooms, you can just pass through the stern engine rooms. So kind of minimum space, but enough because they do basically day trips and everything there back in port. So these stairs take us to the bridge, and this door takes us to the technical space area. There were still some works needed to be done there, but all the electronic components that don't need to be on the bridge are basically here. So this is for Uno, gyros and stuff, some switchboards and some power amplifiers. So this here, what you see, this is a drive cabinet for a SES. So this is where the controls for the dampers and stern banks are. And this here small cabinet with the glass door is actually SES control cabinet, where all the electronics and everything is, and all the connections, and also this is what I mentioned. Also, some improvements were done that ESNA technicians, they have 24/7 access if there is internet available to access the SES system, so they can check, they can extract data to see the performance, and they can also adjust. So they can intervene and check the system remotely anytime, of course, in agreement with the captain of the vessel. So yeah, going back. So this is the door that takes outside. This goes to the staircase that goes to the bridge. So like you said, bridge is cockpit style. And also due to operating in a tropical climate, it had to have double ACs, independent systems. So this is connected to one line of ACs and other, and also connected to different power sources. Class requirements also say that everybody on board needs to have its own seat that satisfy the HSC rules. So these 3 seats are for the crew, and these 3 seats are for the engineer, captain, and the officer that is assisting the captain or pilot. So bridge is also organized as a cockpit style. So everything is basically accessible from a center seat, everything that is important to be used during navigation. On a portside seat, in front of the portside seat are basically controls of the engines. So these are 4 main engines controls, and these are lift engine controls. And behind it, you don't see it, there is a screen of AMS system. And here under it, it's fire alarms and sensors controls. Okay. So from the pilot position, you have instruments like this. So one radar on port side and controls for the radar. One radar on the starboard side, so that's X-band, S-band. You have backup controls for the jets, main controls of the jets, and they are set up that you have, these are combinator controllers, so it automatically puts the bucket up and down, depends what you want to do. And each one is connected to the 2 jets, and they work as one. They work in tandem. So basically, when you turn this combinator lever, jets on port side will turn and do the same one and another. These screens are here are actually controls for the Kongsberg jets. The system that is controlling the jets is an older version, but it's better suited, the best suited from Kongsberg for the quad propulsion. It's a Kanman Touch. So you can see here on both sides controls. In front here, it's actually EGDIS. Vessel is a full EGDIS certified because you don't walk around and put position paper charts at speeds of 550 knots. And we have standard magnetic compass. On this side is, like I said, this is one radar. This is the second this screen. Radar controls, this controls, autopilot. This screen here is, and this is second screen for Kongsberg jets controls. This screen here is actually SES system controls. It's a touch screen. And basically you can set the sensitivity of the system, reactions of the system, ride control, and see the pressures, targeted pressure, actual pressure, and you can see the speeds of the lift fans. You can see the speeds of the stern bag systems and compare the pressure in the stern bag and see this, all stuff like this. But basically, an operator just needs to kind of choose the mode that is going to operate. There's going to be your ride control or motion control. It also has a manual and maintenance settings where you can kind of isolate each piece of equipment that maybe you don't have a good feedback, you don't trust, or you have a problem with. So basically, you can work on one lift engine, or you can work with just one outlet damper, or you can isolate the pressure sensors that maybe they are showing wrong or not calibrated properly. So at least that you satisfy the minimum that the system can operate, vessel will operate. And also I want to add the capacity of the lift fans is that at the expected operating weight of the vessel, so with around 50 tons of dead weight, we have a full redundancy with maximum load on a vessel with about 25 tons of dead weight on board. One lift fan satisfies around up to 90% of the lift, but in practice that means that when the vessel is lighter, with one lift fan working, we can still achieve maximum speeds in what weather allows. If the vessel is loaded until too heavy, then we can still go in a mid 40 knots with the one lift engine. So yes, also standard navigation equipment, radios and stuff. On the other side, also echo sounder, communication PA. We have some fancy equipment like a satellite compass, dueling as a second GPS. Here is a CCTV system. It has 22 cameras around the vessel, outside, inside, in the engine rooms. On the future vessels, and also the modifications are being done on this one to add a screen here behind this overhead console that the engineer could have separate screen just following the engine rooms. Okay, these are indicators for the jets, main engines, heading, and you have here anemometer and speed log. This screen here, okay, the moment was not activated when this was done, this kind of 3D view. This is a Sentry system from CAI, which is actually AI, artificial intelligence camera coupled with the FLIR sensors, with the 4 sensors, two thermal cameras, two IC day cameras, day cameras. So for closer views, further views, basically it's taken from military helicopter sensors, thermal and optical sensors, coupled with the computer and with the software that kind of have a learning sequence and is being updated then and then to automatically recognize objects, but based on a thermal spectrum and on a visual spectrum. Okay, so something that would not be identified on a radar, or it's not sending an ISC signal. There is also added security that actually, and this also comes from requirements, what we should add in case of high speed encounter with the very small fishing boats or some floating objects that you can expect there to have in West Africa. So it's a visual identification system with also thermal spectrum. Secondary is also a security system, because during nighttime you can set it up to rotate 360 and give you warning if there is something approaching, because gives you a thermal spectrum during nighttime, and also identify if it was turned on. It just highlights objects and identify this is a person, this is a boat, this is an unidentified or whatever. Also, third use for this, and this was important also to present to the end client, is a thermal difference imaging, because it has a 0.02 degrees sensibility on a closer ranges, so up to 200 meters. And that was important when you are approaching offshore installations. In case of fire, there might be something burning, but it's not a visible fire, or high temperature emitted. So you cannot risk approaching with a 60 to 80 passengers on board of something that could explode any minute. So that's where it helps and gives you that thermal image of the installation, so where you can go or not. What else? The standard radio set is GMDSS area A3, because it needs to go that far from the shore. Going out, so standard equipment added Starlink antennas, VSAT. Behind it's also Iridium. There was a lot of issues with vibrations with the equipment, because we have a lot on a main mast. So we had to kind of add some securing wires to it and so on, because there was a resonant vibration that was mainly damaging the supports for the SATCOM C antennas, the ones that are on top. So that was also some lessons learned. So yeah, that's it basically, how the vessel looks like. I can show you also how it works today. Just let me. So we actually had to okay. We actually had to keep low profile until the owner decided to promote this vessel, and this was after more than a year of being in construction. So we were very eager, and this was actually for us was a bad thing, because we wanted to promote, we want to be allowed about it. But actually, what was a breakthrough was this video made by a fisherman catching what is it? I don't know, some big fishes in Singapore Strait. And basically what he says, and you're going to hear, he talks Malay. I don't know if some of you talk Malay. He says, "Where is this idiot going so fast?" But this was actually first came out, and until today on Facebook and on Instagram, it has on each one like 3-4 million views, and he's just a fisherman. Yeah, so this is it. And So basically, this is during initial tests, the vessel is going around 43, 44 knots. And we passed maybe 100 meters from him. Okay, how the vessel are doing today? He can show you. Okay, just a moment. This was what I'm going to show you. This was filmed by my colleague Jerome. This is actually two of Aircat's meeting, one going to the field, one coming back from the field. He came out, which was not smart, at 40 something knots to film the vessel. You can see that he's hardly holding the phone stable and holding himself not to be flown off the deck. So this is in Angola, and this is about 1 month ago. So both vessels are going in a 40s plus speed. It's actually relatively easy to identify the speed of the vessel by the wake that it makes by the wake that it makes when sailing high speed. And for example, on this video, this is a promo video that we made, probably used so. Okay. I can. Maybe this is too noisy. So this was in shipyard. This is how they were lowered. This is when it's full lifted. So here, okay, here is going around 45 knots because there is not too much wake on the side of the vessel. All wake is kind of behind it. But for example, on this one, you can see there is, okay, I'll stop it at the moment. Okay, so here you can see actually that this is going much faster, much slower, sorry. This is in 32, 33 knots because you can see that the wake is on the side of the vessel. There is a lot of white around it, a lot of foam created. So although it looks nice and impressive to some people, I don't like it because it means it's slow. So, yeah, but you will see on some other views. Okay, this is a full speed circle in calm weather without reducing speed, so anything. So coming into turn with the 49 knots, and usually we would come out somewhere around 40 knots when we finish 360, but the turning circle is more than 200 meters in this case. If you want to make a short turn, you need to slow down and kind of let it cut into the sea because here it's still a little bit sliding. So this is a slower speed circle. Okay, so the issue why somewhere you see it going slowly and somewhere you see it going fast, and that's how you can identify due to disturbance that it creates in the water around it, is because the drones could not catch up. And we were doing a promotional video, and drones just could not follow it because the standard filming drone they do like 30 plus knots, so they cannot follow the 40 something vessels. So we had made several tests, and in the end we used a racing drone that we attach a camera to it, and that drone can do above 50 knots, so it could follow the vessel. But the problem is that that drone then could fly only up to 5 minutes. So we had less than 5 minutes to speed up, slow down, and get the drone back. Otherwise, we would lose it. So that that was a very interesting thing to know. Uh, I can also show you how the vessel is working. I can show you how the Tesla is made first. Okay, sorry. I don't know if you are seeing this. Okay. So this is just model testing. Of course, it doesn't have a full functionality. Tests were done in Stad Tank in Norway. And this is comparing a vessel that uses the cushion and not using the cushion, but you don't have all these ride control, pressure control systems. It's just a cushion or not. So you can see the difference, how much one gets into the water and the other one. So this is a standard. And then you have comparison, how much you compensate. In reality, with active motion damping, when stationary, we reduced more than 50%. Motion sickness index, or how much people vomit over a certain period of time, we reduce about to 40% compared when we use motion damping compared to when we do not use. So the system, when it's active, when it's compensating for the heave, it kind of compensates a lot. So I can show you how this looks in practice. Just this. Okay, this is transfer of the people. You can see it's very steady, very comfortable. Okay. And also I can show you how it, there is a better, just, yeah. Yeah. So this is now showing how it holds. You see it's very steady, pushing onto the guide pipes of the boat landing, but you can see how the water moves under it. And now we have a heave compensation. So the computer is controlling opening of outlet dampers, and it's compensating for the change of level of water due to waves under it. So you can see that also you see some spray coming out when there is a wave through, but you see that water moves about 2 meters, but the height of the bow pushing on a boat landing structure stays as the same level. So we can compensate easily to wave heights up to 2 meters if they are not too violent. So 1 meter, 1.5 meters vessel does not feel, nothing happens. It's very wide, and there's no pitch. There is a little bit stern work, but that's not important because the bow is important. That bow doesn't move and people can walk off, walk on safely through the bow. What else I can show you? How it looks in Angola today. This was just a moment, not this one. Just give me a moment. Which one is it? Okay. This is in Angola. This is navigation. Here is going like 44 knots something. And you can see that is relatively comfortable. The weather here is good. There is some long swell sideways, but there is no live seas. So that this was easy for the vessel. But this is one of the first operations, so that was 44 knots. What else I have for you here? I can show you some images. Just a moment. This one. So this is when they were installing the lift fence. This is in a hangar in a strategic shipyard. You can see the other vessels just there ahead. So there are all three built. So that's this is a number one. That superstructure that you see behind is number two, and here the lower part of the vessel, so the hull is a number three. That's energy craft 3514 what else I have here? So, do you see this one? This is when the. Do you see this one in the hull? This is when the fan is installed through the hatch. So basically, you don't cut anything. You just open the hatch, put it in, take it out. That's it. So, and that's also what dictated the shape of the hull itself. Yeah.
Okay, Edward, bearing in mind the time,
Yeah.
perhaps we should.
I talk too much.
No, absolutely not. This has been a very illuminating presentation. But I do want to give the people present just a chance to ask you a question or two
Of course,
before
yeah.
break up. So if I can open it up for questions, and first of all, you'll have to unmute your mics when you want to talk. Who would like to go first? Or have we been assaulted by so much technical information that we're almost in overload at the moment? It's absolutely brilliant presentation, Edward.
I just
gives a
prepared
good
some
view.
videos, but I could talk about this for hours because that's been my life. Yeah.
If I could just ask one question, Eduard. In the 60s and 70s, we had a maintenance operating issue of 1 hour's engine operating, 5 hours maintenance. What is the ratio of the AC-35?
For the maintenance of the engines or all vessels? So
well, it would be the vessel, because if we operated the engine, it was operating the whole craft. So for 1 hour's operating, we had 5 hours maintenance. Yeah. What ratio would be on this craft?
Yeah, I think if I could help it,
you're working at nearly 100% all the time, 50 hours a week.
Yeah, what Mike is on about is, of course, military craft, Edward, rather than commercial craft. So there's a much higher ratio of kind of daily maintenance and so on. But yeah, what is the expectation for these vessels?
Well, these vessels are planned to have a 1 day of maintenance per month. So in 1 month, they are going to work, let's say, that would be like...
Nearly...
Sorry?
Working a lot of hours, because there's about 200 or 300 hours of operating.
There is okay, I don't have it now in my hand, and there is a planned maintenance that must be followed by the engine maker, MTU.
Yeah.
Right.
But engines itself are designed, are dimensioned, and also power limited, so they can do this 100% MCR. So they are going to do all the pre-checks every day. They are going to do weekly. Because they have 1 day maintenance, so they're paid free of whatever they need to do. but every week they have one day that they are not going out. So in this one day, it's going to be their day of changing the filters, checking the filters. But just keep in mind, the system is different. So,
completely. Ours were gas turbine engines.
Of course.
We're talking diesel engines.
Yeah, these are diesel engines.
Yeah.
Later generation. All the filters and everything also are double. Okay, so there's no single line. You just swap the filters and stuff. So they need to kind of check it. Also, that I did not mention, due to particular reasons in West Africa, you can also have some bad fuels, dirty fuels, bacteria infested fuels. These vessels have actually in each hull complete purifying station.
Yeah.
Which is based on filters, not centrifugal purifiers, and that are made to extract water residues and also all the particles that you might find. But the capacity of each one is to fully support the whole needs of the vessel plus 20%.
Yeah.
So you just need one to operate the whole vessel. But also the origins of this came from and they are made by Relumix. That's a French company that makes fuel purifying stations for their Charles de Gaulle aircraft carrier, but fuel for jets.
Yeah.
So that's actually the origin of design.
Yeah.
And so we have, like I said, there is a lot of redundancy, and also on this there are redundancy because you have all the filters, all the lines are doubled, and all the filters are switchable. So in that sense, the maintenance of the engines, there is nothing particular that you need to do. You just need to check the filters from oil filters, fuel filters, air filters, and then about 3,000 hours you need to do some throughout checks. But also, like I said, we kind of drift away from the maintenance on board, because these vessels are going to be in port every day.
Yeah.
And there is a short team, and there is whole set of spare equipment that we made it kind of swappable. So it's kind of different.
Basically, follow the manufacturer's instructions.
Yeah. It's strictly because also hits into guarantees, and it's everybody interested that these vessels perform. Yeah. They need to perform for a whole duration of the contract, which is 5 years.
Yeah.
So there is just no place to play with this.
Yeah. Okay. Fine. Thank you.
Yeah. Welcome.
James, I wonder if you have particular thoughts at the moment, these being very advanced vessels for strategic marine. Can you unmute? You need to unmute your...
There you go.
Hi. Okay.
Yeah. For us, it's been a great project. Eduard is way more in the detail. I wasn't on the project team. I'm in business development for strategic marine, based in Europe. So Eduard knows it all intimately. But I was on one of the sea trials. I've been on the vessels. They're superb. It's great to go 53 knots and still standing up drinking a cup of tea. That's very, very impressive, and it's produced quite a lot of interest from the market, as you can imagine, and quite a lot of my day, although these are being used in Africa and oil and gas, quite a lot of my day is taken up talking about wind farm vessels. So there's a lot of interest with this type of platform for offshore wind as well, where they're looking for more speed as the wind farms go further offshore. And all the current wind farm CTVs go, let's say 25 knots would be standard, and actually they would probably operate in low 20s. So for a vessel that is a step change in speed, it's generated a lot of interest there. But it's great. It's great for us because they're such an unusual hull form, and you normally have to explain what an SES is to whoever you're talking to. It's very rare that someone says, "Oh yeah, I know what that is." Yeah, it's interesting.
Thank you for that, James. And
that's right.
So this the recording here gives people a way into all the technology with Eduard. Anybody else would like to question or comment?
Yes, can I ask Eduard about the lift fans? You mentioned there was an issue with spinning the fans up and not enough torque from the engine. Do you think that's due to the weight of the fan or the rotational inertia of the fan, or is it the aerodynamic loading of the fan that's overloading the engine?
Well, I cannot say that it's one or the other. Okay? I think it's a combination of the things. To our findings, it's not the weight of the fan, but we all noticed that it behaves very much differently if the inlet damper is open or closed. So actually, it was harder to have a proper start when the inlet damper was open, because that was forcing lift fan to push more air because it was open, and that was creating more load on the engine. And at the low RPM, engine was having issues coping with it. So we would have sometimes a shutdown or instability of the whole setup. But like I said, adding a trolling valve and adding a startup sequence that we kind of tested, measured, and kind of provided enough time to kind of slowly clutch it in with different pressures to allow lift fan to speed up. It's very smooth. So now that is like, you don't know even that is happening. Only difference how you know that the sequence is done and everything is completed is when you have on a screen on a bridge that is on, for example, RCS mode, ride control system. So that is ready to go. So that's it.
Eduard, I have several questions.
Yes.
And enjoyed your presentation very much, and I'm surprised at the degree of sophistication that's involved in these vessels. They're extremely complicated, and obviously a lot of engineering required. My interest is in the skirt system, which hasn't been mentioned, so I'm interested to know, first of all, what's the life of the skirt system, and how do you go about maintaining it? And roughly what sort of materials are you using? How thick are they? Appears like there's segments on the front and a bag skirt on the back from looking at the underhull views. I'm also interested to know if the bag has internal bracing, or is it just a very simple loop bag?
Okay, so bag itself, the materials that are used are identical on a forward skirts and a bag. These were the supplier selected for this Checkmate. Okay, so fiber reinforced rubber, same like is used on a hovercraft, as far as I know. The thickness is 2.6 millimeters on the bow, but the lower part is originally distributed as doubled. So each skirt finger is basically triangle shaped. I can show you here. Triangle shaped piece of rubber slided in through the guide frames welded on a wet deck. Just a moment. Okay, so they're just welded here guides, so and bolted on front. On the tips, on the lower part of this skirts, they are doubled originally, and they have bolted pieces inside. Okay, and as they get consumed, when they are over-consumed, that the vessel could not lift due to leakage of air under the skirts, you just unbolt and put a new piece on it. Now, how long it will take to replace each one, meaning hours of navigation, we are actually not sure, because it changes with the environment. Experience show that, for example, compared to the Seawind Pioneer, which is a bit slower vessel than this, Seawind Pioneer was in high 30s, around 40 knots sometimes, but it was operating also in colder areas. As far as we know, they never changed the skirts, so there was no issues with them. In let's say they had stop and goes, some issues, but let's say 1 year of operation, they did not change. As mentioned also from machinery, also the complete sets of skirts and bags and the replaceable fingertips for a bow are actually supplied with the vessels. To replace the fingertip, basically you come with a small dinghy, you just hook it out of water, so it's not that heavy, you can lift it by hand, and you unbolt. There is a set of bolts. You unbolt the consumed part, lower tip, and you bolt the new one, and you put it down. So to change complete set of 7 that are on these vessels, it takes you about a day. On a stern bag, I need to show you. I think I have a separate presentation video. I don't know if I have it ready. Sorry. Stern bag is actually 3 lobes. 3 lobes of rubber skirt. Sorry, just 3 lobes of rubber skirt, but inner ones are actually inner ones. Inner ones are actually not hermetically closed. They have openings in them, just round holes, a lot of them. So the air passes through all 3 lobes. Only the outer one and the back part of it is fully closed. On the sides of the stern bag, it's just touching the side of the house. There, it's not. It's open, just touching the house. On stern bag, we don't have during the at least life of the vessel until first dry docking, which would be, let's say, 5 years. We don't have expectancy to replace this stern bag unless it's physically damaged. And also we have experience on other vessels when the bow skirts are damaged. If one is damaged and 2 next to it are still in good condition, they just replace the volume. They just inflate, become thicker, and close the gap. So, yeah. You said.
Okay. Yeah, I think we ought to think of bringing this to a close. But okay. Just because we moved on quite quickly, Malcolm, were you happy with the explanation on the fans, or yes, like to say something more? Yeah.
No, that's very interesting. Thank you. That's all I need.
Yeah. Sounds like there's something to work on there. and aerodynamically at least. But yeah, I think Mike Mooney, that is. Could I ask you to bring us to a close?
Yeah, sure, Alan. I'd like to thank Edward very much for a very comprehensive and in-depth presentation of the craft and its capabilities. 40 knots, 50 knots seems quite fast even for an SES, but congratulations on achieving it. It's a fantastic project.
Yeah.
Thank you. Thank you very much indeed. I think, yeah, I have my own thanks, Edward, and also to Jerome, because he offered in the beginning. Hopefully we'll have another talk sometime later on further SES from Aircat.
Yeah.
In the meantime, gentlemen, I will bring this meeting to a close. Thank you very much, all of you, for attending. I hope it's been interesting to all of you, and hope to see you soon.
Thank you very much, everybody.
Thank you. It was a pleasure.
Bye.
Thank you very much. Thank you very much.
Edward.
Bye-bye.